Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden we realize we may have to rewrite all the textbooks about the beginning of the universe. Now, it takes many billions of years to create a galaxy like the Milky Way galaxy.
This is what renowned American physicist Mr. Kaku had said a year ago. Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe. Now, it takes many billions of years to create a galaxy like the Milky Way galaxy, with 100 billion stars many billions of years old. But the James Webb Telescope has identified 6 galaxies that exist 500 million years after the Big Bang that are up to 10 times bigger than the Milky Way galaxy. That shouldn't happen. There should not be primordial galaxies that are bigger than the Milky Way galaxy that are only 500 million years old. Something is wrong. We may have to revise our theory of the creation of the universe. More than 2 years after the successful launch of the James Webb Space Telescope, astronomers are now enjoying a fruitful period of discovery as the telescope pushes the limits on what we can see. But the discoveries have also opened a Pandora's box of conundrums for cosmologists. Recently, the telescope's observations once again entered the first 500 million years after the Big Bang. And this time, it observed galaxies that are most definitely anything but infantile, as in, they are extremely massive and mature, far more than previously expected for such early times. Now, astronomers are staring at a galaxy that could be one of the oldest ever, and the shocking part is that it already contains billions of stars. Interestingly, only 2 years ago, the Hubble Space Telescope spotted this cosmic giant as an unusual point of light in its field of view. Scientists couldn't have imagined that this odd speck of light is a monstrous galaxy lurking at the edge of time until they turned Webb to look at it. Webb's observation revealed that the point of light is actually a primordial galaxy that is far more massive and mature than it should be. Dubbed GZ9P3. This galaxy is at a redshift of Z equals 9.3, which means we are seeing it as it was only 510 million years after the Big Bang. Now, we have spotted other galaxies as they were around 350 million years after the Big Bang, but none of them are as massive as this one. Together, these findings imply that stars within the galaxy must have formed more rapidly and effectively than previously believed in order for the galaxy to attain its current size. But that's not all. GZ9P3 also has a strange shape that might be giving away the early universe's secrets. The team behind the discovery found that the galaxy has 2 bright patches within it, revealing its 2 dense nuclei. This most definitely points towards a galactic merger, 2 primordial galaxies smashing together in the infant universe. What's more, the team not only identified the age, mass, and shape of this ancient galaxy but also zoomed into its stellar population and found that young, bright stars dominate the galaxy's image. The study team used the JWST to find specific elements like silicon, carbon, and iron in the oldest stars of GZ9P3. Iron is the heaviest element stars can make. When these stars exploded, they spread these elements into space, enriching the early universe with metals that later became part of new stars. They also found that there were more old stars in GZ9P3 than they thought. This suggests that galaxies may have become chemically mature quicker than we thought, with stars enriching the universe with metals faster than expected. The unexpectedly mature, older population of stars in GZ9P3 challenges our current understanding, suggesting that stars formed much earlier than previously thought to have aged sufficiently by this cosmic time. These findings imply that a new model may be required to explain the rapid growth of galaxies to such a chemically mature state. In addition to their surprising size, they also imply that galactic mergers may have dominated the universe immediately after the Big Bang. Our current cosmological framework may not be incorrect, but our perception of the rapidity of galaxy formation likely needs adjustment, given that these galaxies are more massive than previously deemed feasible. Even though we have built our cosmological model based on observations and theories and mathematics supporting those theories, there are a few clues that the universe isn't completely adding up. You may have heard about the crisis in cosmology. Well, basically, the crisis originated when different methods of measuring the age of the universe started giving different results, and still do, and cosmologists have no idea why. The James Webb Space Telescope, with its recent discoveries, has worsened the crisis even more. The universe is expanding, and distant galaxies are moving farther away from us. When we calculate the rate of the expansion of the universe using the cosmic microwave background, which is the light left over from when the universe was only 380,000 years old, this is what we get. Then there's another method where we know how bright distant supernovas are supposed to be, and we can compare that to how bright they appear when we measure them. We can then use that information to estimate the expansion rate of the universe at the time of the supernova. When we calculate the expansion rate using this method, also called standard candles, this is what we get. So, the expansion rate of the universe is called the Hubble constant. However, the difference between the results of the two methods is called the Hubble tension. And this, my friends, is the crisis in cosmology. But this is not the only crisis anymore. A recent cosmological distress has emerged, challenging our models like never before. I spent all my life developing a particular theory of the universe, and now that theory is being questioned. I welcome that because that's how we move forward. That's how we make progress in science, said one scientist. When you look up in the sky, given you are not in a city or place obstructing starlight, you see countless stars. You also see the Andromeda Galaxy as a smudge amidst the many stars. That's because the universe is filled with stars and galaxies. The question is, how much of the universe do they fill? In other words, how much matter is actually there? A simple question, the answer to which is anything but simple. This dilemma exists largely because current cosmological observations simply disagree on how matter is distributed in the present-day universe, and this has given rise to the mysterious S8 tension, aka the new cosmological distress. Now, the S8 tension is a measure of the lumpiness or clustering of matter in the universe. To put it simply, picture the universe as this colossal puzzle where the pieces of matter are scattered throughout space. Scientists want to understand how this matter is distributed and how it clumps together. There are two ways to measure it. First, by precisely calculating it using low redshift observations such as weak gravitational lensing. Gravitational lensing is a phenomenon where the immense gravitational pull of massive objects like black holes and galaxies act as cosmic magnifying glasses, bending and distorting the light from more distant objects that would otherwise be invisible, providing unique insights into the vast universe. However, the S8 value derived from the second method, which is the standard model of cosmology based on cosmic microwave background measurements, does not align with values obtained from low redshift observations. This discrepancy forms the perplexing heart of the S8 tension. Now, what do we do? Clearly, there is something that we do not understand at all, something that isn't quite adding up, despite the countless theories and observations and hypothetical entities supporting those theories. What is going on? To find out, astronomers used one of the most powerful supercomputers in the world to carry out the largest cosmological simulations ever. One cannot even fathom the scale of this project until you realize that the simulations required a total of more than 50 million hours of computer time, distributed over the 30,000 processors that make up the DAC Cosma 8 supercomputer at Durham University in the UK. The project is called Flamingo, a convoluted acronym of Full Hydro Large-Scale Structure Simulations with all-sky mapping for the interpretation of next-generation observations. Apart from its huge size and high resolution, Flamingo sets itself apart from earlier simulations by incorporating much more than gravity alone. Up to now, most of the cosmological computational simulations of our universe focused on modeling dark matter only, as it is the main matter component. However, even though normal baryonic matter makes up only 1/5 of all the mass in the universe, it can have a big effect on how cosmic matter is distributed at small distances. For instance, galactic winds powered by supermassive black holes and supernova explosions may stall the growth of galaxies. And unlike previous simulations that only considered dark matter, Flamingo takes into account and tracks ordinary matter too. Because although dark matter dominates gravity, the contribution of ordinary matter can no longer be neglected. While the simulation marked significant progress, like accurately matching the formation of the Milky Way and the Andromeda Galaxy, amongst many others, it fell short of explaining the observed weak clumping of matter in the present-day universe. In other words, it failed to resolve the very thing it was created to help solve, the S8 tension. Or might I say that the Flamingo simulations may be indicating that something is terribly wrong with our cherished standard model of cosmology. The simulation also contradicts the observations of the Webb Space Telescope and other observatories about the distribution of matter in the universe. The current theory beautifully explains how galaxies evolved, but there's a problem. It predicts that they're 7% more closely clustered together than they actually are. The new computer simulation is much more detailed, and it takes into account the role of supermassive black holes, but that's not right either. It's still 5% more clumpy. Recent observations from Webb have proved that the Hubble tension actually exists. That's right. The James Webb Space Telescope has cross-verified the findings of its predecessor, the Hubble Space Telescope. The pioneering observatory discovered that Hubble's calculations of the universe's expansion rate are exceptional, intensifying the so-called Hubble tension. In essence, measurements of the universe's expansion rate, defined by the Hubble constant, simply do not align. Nobody knows what is causing it, but some hypotheses call for new physics to explain the apparent contradiction. With measurement errors ruled out, what remains is the intriguing and exhilarating possibility that we have misconceived the nature of the universe. New theories are already making their way into the limelight, with some calling for the removal of dark matter. What do you guys think? Drop in your comments to let me know. And don't forget to subscribe us because this is your go-to channel for the latest in space discoveries and cosmic mysteries.